Hi class, this is Gigi, and I am going over graphing functions. This is example number 5 in your note packet. Okay, so graph the function f of x is equal to e to the negative x squared. Now this function is a famous function. It's called a normal distribution function. You have seen statistics or have taken statistics, you probably have heard of this function. Anyways, first, let's look at the domain. X is up on top of at the exponent, and then x is being squared, so that is always going to happen. So domain would be negative infinity to positive infinity. And then second, we want to look to see if there is symmetry. Okay, so let's look f of negative x, and if you mentally look at it, if you plug in negative x and you square that negative x, that is going to be x e to the negative x squared, which is the same as f of x, right? So what does that mean? What kind of symmetry will it have if f of negative x is the same as f of x? If you think about it, right here, here's x, and let's say f of x is right here, right? And then here's negative x, and f of negative x is the same. So that means we have symmetry with respect to the y-axis. So if we just graph one side, the other side will look just the same, right? So symmetry with respect to the y-axis. Okay, so that's something that we can do so that we can shortcut this. We only need to graph on the right-hand side or the left, whichever you want, but I'm going to try to stay on the right so numbers are positive. And then the left-hand side will be exactly the same. Okay, number 3, critical points. Critical points is when the derivative is 0 or the derivative is undefined. Okay, so let's take the derivative here. F prime of x is equal to the derivative of e to some power is exactly the same, multiplied by the inside derivative, which is negative 2x. So that really is negative 2x e to the negative x squared. When is that equal to 0, and when is that undefined? Well, that thing is always good, always defined. So we don't need to worry about when the derivative is undefined, because we can always use x as a function, or we can think about it this way. This is the same as negative 2x over e to the x squared, right? So e to the x squared is never going to be 0, so we don't need to worry about that being undefined. However, f prime of x is equal to 0 when x is 0. So critical point is just x equal to 0. Okay, has symmetry with respect to the y-axis, and the domain is all real numbers. That would be 1, 2, 3. So we're going down the line here. Possible point of inflection. In order to do that, we would have to take the second derivative. So the second derivative of x is product rule or quotient rule, whichever you like. I think I'm going to do the quotient rule because I have it written right here as this. So that would be negative 2e to the x squared minus 2x e to the x squared multiplied by negative 2x, all divided by e to the x squared, all of that square. And when we reduce, we would say that would be negative 2e to the x squared minus minus is the plus 4x squared e to the x squared divided by e to the x squared square. we can now reduce each one of those, have an e to the x squared. So that would be just -2 plus 4x squared all over e to the x squared. So that second derivative is equal to 0 when 2 minus 4x squared is equal to 0. That is when x squared is equal to minus 2 divided by -4 reduced, that's 1/2. So that means x is equal to plus or minus square root of 1/2, rationalized to be square root of 2 over 2. So those are possible point of inflection. Okay, so then we would go and check for our extreme values. So that would be, now we would check for increasing, decreasing, and then we would check for concavity. Okay, so I'm going to go ahead and put that on a number line. So here we go on a graph, or actually we can actually put that on a graph because we know how that kind of should look like. Here is 0. And that is one of the critical points. And then here is square root of 2 over 2. Here is negative square root of 2 over 2. Those are possible point of inflection. And then 0 is critical value, right? So I'm going to keep these in a box because that are possible point of inflection, whereas 0 is the critical point. So if we look at the derivative, when x is a negative number, -2 times a negative number is going to be positive. Okay, and then positive number divided by x, e to the x squared, which is always a positive number. So we would say f prime of anything to the left of 0, let's say -1, you are going to have a positive over a positive, which is a positive number. So your function on the left-hand side, left of 0, it will be increasing. So I'm going to go ahead and write increasing here. Actually, I'm going to write it below. Increasing here, increasing here. Right? Anything to the left of 0, it's increasing. And then if you have any positive number, really, -2 times any positive number is going to be negative on the numerator, and the denominator is always positive for the first derivative. So then the first derivative is negative to the right-hand side. So this is decreasing, and then it continues to decrease. Okay, now we are looking at possible point of inflection. Okay, so possible point of inflection is when we are talking about the second derivative. Okay, so we are looking at the second derivative here. We will look at the second derivative, and let's go to the left of square root of 2 over 2. Square root of 2 is about 1.4 divided by 2, that is 0.7 roughly. But if I was to go all the way over here to the left-hand side, I'm just going to go ahead and pick, say, -2. Okay? Now, when x is a negative number, -2, you have -2 plus 4 times a -2 squared all over e to the 4th power. Now, I didn't really have to write that down, but here it is so you can see. -2 squared times is positive times 4 is going to be bigger than -2. So that is a positive number, and then e to the 4th power is positive. So that is a positive overall. So this is going to concave up, increasing, concave up. Okay, now we have a number between 0.7-ish to 0. Let's pick negative 0.1. That's easy to do math with. Okay, negative 0.1 square. I'm going to go ahead and write that down to negative 0.1 square, all divided by e to the 4th power. So that right there is going on the numerator is going to be a number less than 2. Minus 2 is going to be negative, divided by positive, it is a negative. So this is going to concave down. So this right here is a point of inflection. Okay, similarly, if we are looking at, when we are looking at f, this is second derivative, not the first, sorry about that. Even if it was a positive 0.1, we are going to end up with the same value because the x is being square. So we still have negative over positive, which is negative. So this right here is concaving down. And then if we pick a number to way to the right of 0.7-ish, then let's pick 2. Then we will have, again, the 2 is being squared, so that's going to still be positive over positive, which is a positive number. So this right here is going to concave up. Okay, so let's go ahead and look at the graph of that. And we know that it's increasing, decreasing. So we have right here at 0, we have a relative mass. Okay, right there at 0. Now let's go ahead and sketch the graph. Concave, increasing, concave up, and your function as x goes to infinity, and this is where we're going to go ahead and look at the domain and range. Okay, so we'll already look at the extreme value, and we're going to go ahead and look at the end behavior of the function. In this case, it doesn't, the function f of x is equal to e to the negative x squared. That's our function. That is not going to have any vertical asymptote. However, the limit as x goes to infinity of, and I'm going to write that as 1 over e to the x squared. When x is going to infinity, x squared is going to be really big. 1 over a big number is going to be 0 roughly. So the limit as x goes to infinity is equal to 0. So that right there is our horizontal asymptote. And even if we were approaching negative infinity, we would get the same value because x is being square anyways. And so we have horizontal asymptote as x equal to 0. Okay, so here we go. We're not going to cross the x-axis, and we are going to increase. And then right there, we're still going to increase, but now it's going to concave down. Right? So it would go like that. Okay? And then here we're going to decrease, concave down. And remember, it has symmetry, so it looks exactly the same as the other side, right? So I'm going to go ahead and make that point there. And then this right here is decreasing, concave up, and then it's increasing, concave down. And that right here is a point of inflection also. And this right here is our relative, actually that right there is the absolute max. That's the maximum that there is in that function. Okay, so that is the graph of the normal curve. Now, if you really want to know, that exact value right there, then you could go ahead and plug in 0 for x, right? So if we plug in 0 for x, we would say f of 0 is 0. That really is e to the 0 power, which is 1. So that right there is 1. Okay, that is how the normal curve looks like. So that should give you an idea of how to sketch the function, right? And that when I plug in 0, I got the y-intercept. There's no x-intercept because the x-axis is your horizontal asymptote. And if you need any other point, then you would do so, but we don't really need any other point. We could sketch the curve. Now, if you really, really, really wanted to, you should find this point and the value of that point so that it would be a little bit to scale. But as far as the shape goes, I think we're happy with that shape. Okay?